Let's first do a recap of what we did in the previous lecture. So the entire procedure of the Carotheo-Doré theorem starts with first we have a function defined on a collection of sets. Basically, we want to assign some value to these elements. So here we require the entire space is in the set E. And then from there, we extend and we define an outer measure using this function. So outer measure is defined on any subset of X by using this infimum of the open cover, or not the open cover, but the E cover basically. So you have the summation of f of EI, where A is basically covered by this union of EI. I is countable here. All right, so there we showed that this mu star is always an outer measure, but it's usually pretty large, so we need to drop it to a smaller sigma algebra, and we will get a measure. So we'll get a measure by only restricting this mu star on the sigma algebra that's mu star measurable. So this is the Carotheo-Doré theorem. All right, there is one problem with this construction. You see this function f here is very arbitrary. It can be anything defined on this collection of set E. It doesn't even have to make too much sense. The f itself doesn't have to satisfy all the additivity, the sigma additivity, and so on. So you would imagine if you have a very arbitrary choice of the f, and now you drop it to this mu star, so in this step, all the information of this f may be lost. Okay, so there are many sets inside E that may be assigned a different value using this mu star. So let me maybe give you an example. So this is a very easy one. So let's just consider a very simple set where the X only has two elements. And the collection of E, let's just say E is the entire collection of subsets of X, so it contains A, B, and AB as a set, and then the empty set. So now I define this function f, so this is going from 0 to infinity, so this is the function f. You will need to map empty to 0, that's quite clear, so let's give some value for AB and the set AB. Let's say, well, this is mapped to 1. This is mapped to 2, and then AB, the entire set, is mapped to 1. All right. So let's see what will happen. Well, if you run through this procedure and we want to define this mu star, okay, so the mu star here. So mu star, let's use a subscript of f, is basically the minimum of these f value of each cover. So the mu star will map the empty to 0, that's pretty clear. It will map the entire set AB. Well, there are two ways to cover the set AB. You can use AB set AB, or you can use set A and then union set B. And as you can see, if you just use the set AB, then it has a smaller f value, so this cover has value of 1. So that's is going to be defined as the mu star of this set. And then if you look at the set A itself, okay, so if you just look at A, well, then the only cover that's, well, there are only two covers. You either use A to cover A itself, or you use AB to cover the set A. And either way, you will get the value of 1, so that should be the smallest. And finally, if you look at the set B, if you want to cover the set B, well, you can use B, or actually have a smaller cover, you just use AB. So you can convince yourself the outer measure will assign a value of 1 for the set B. Okay, because AB, this set, is already a cover of B, which has f value 1. So this is how, running through this procedure, you will get this mu f be this map. And as you can see, the only mu measurable set, this collection, you can convince yourself there are only two things that are actually mu f star measurable. That's the empty and the whole set. Either A or B, they're not measurable because if you take A and, well, if it's measurable, then a complement has to be measurable, but you add these two up, it doesn't add up to the measure of a B, so A itself is not measurable in this case. So in the end, using the Carathéodory, the mu of this, the measure of this whole procedure, basically only says, well, these two are measurable and has value 0 and 1. The singleton A and the singleton B, they're not measurable. And as you can see, well, even if you forget about the Carathéodory where you drop these two singleton sets, you can see that the map, this mu star, already lost the information of f of b when you try to look at the outer measure of the singleton set. So this mu star may lose a lot of information of f, so it doesn't need to agree with f at all. So that's now something that we like. So we want to say, well, in what circumstance can this outer measure kind of preserve the value of this f we assigned? Okay, so that's kind of the motivation behind this definition of a pre-measure. Okay, so let's give the definition. So here is the definition of a pre-measure. So suppose we have an A, which is an algebra. So a pre-measure is a function that maps A to 0 to infinity. So here again, we allow a set to take the value infinity. So here the pre-measure needs to satisfy these two conditions. So first of all, it maps empty set to 0. That's quite standard. And second, suppose I have a collection of disjoint subsets, and suppose their countable union just happens to be in this algebra. Remember, an algebra, not a sigma algebra, this countable union doesn't have to be in there. So we're saying suppose this countable union is in there, well then this mu on this countable union, let's give it a name, let's call it A. The mu of this countable union has to be equal to this infinite sum. So this mu itself is not going to be a measure. It's only defined on an algebra instead of a sigma algebra. But the pre-measure is basically saying, suppose your set looks like some, let's say this A looks like an element in a sigma algebra being a countable union of some disjoint set, well then your mu has to behave just like a measure. It needs to satisfy the sigma additivity. And just want to remark on one thing. Because the empty set is being mapped to 0, this mu will satisfy the finite additivity. So suppose you have two sets A and B, they're disjoint, then you know this A union B is inside the algebra A because A is closed under finite union. And then this mu of A union B, well, you can just say, well, this A union B, you can treat it as A union B and union a bunch of empty sets. Well, the empty sets are all disjoint with A and B, so this is, by definition, this is equals to mu of A plus mu of B plus mu of the empty set, which is equal to 0. So the mu of A union B is mu of A plus mu of B. So now you have the finite additivity. All right, so what's so good about these pre-measure is that if we run our procedure, we start from a pre-measure, and then we define an outer measure from this pre-measure, and then we get a Carathéodory theorem to get another measure. Then this measure will actually extend our pre-measure. So the information of this pre-measure is all preserved. So let me state the theorem. I'll leave the proof to the next video. So suppose you start with a pre-measure on some algebra, then Now you run this procedure, you generate an outer measure based on this pre-measure you define as the infimum of the covers. And then you apply the Carathéodory theorem to get a complete measure that's basically all the mu star measurable sets, that's the sigma algebra B, and then the mu bar is this outer measure, mu star restricted on this B. Then now we have a theorem that states the following. So first of all, anything in your algebra to start with will be mu star measurable, so it will be contained in the sigma algebra B. And second, the measure mu bar you obtained from the Carathéodory theorem, that will actually extend the pre-measure mu. So if you restrict this mu bar to your algebra, then you actually recover the original pre-measure mu. So in other words, all the information of this pre-measure is now preserved using this Carathéodory theorem. We'll leave the proof to the next video.